Dr. Mitsufuji is a distinguished engineer from Sony Group, and he's very well known for his work on AI for music and gaming, which are both my favorite topics. So let's welcome Dr. Mitsufuji.
Thank you, everyone, for having me today. My today's talk is mainly about audio-visual models and also some defensive research for creators. But I, just used a general title that could be applicable to anything here. So just go to the next slide. Okay. So myself, I've been in this, audio field for more than 20 years. And now I'm based in New York. The office is right in front of Madison Square, not garden, the park, yes, the park one. And our team is, the majority of people are in Japan, but we just launched our New York office. And we also have some people in Europe. So in total, it's like 60 researchers across the world, and working on not only audio, but also machine learning, computer vision, and NLP. And I see some of some folks from New York University, but I just started visiting research professor position at Marl. I think I can find one there. Okay, here you go. So yeah, we're gonna work on some spatial sound research. And I also want to advertise this work. Recently, open at SNS. It's called The Principle of Diffusion Models. It's monograph. And it took us actually almost 1 year to get prepared for publications. And we believe this could serve as a Bible for diffusion. So it has 457 pages. But it's nice for summer vacation, winter vacation. Yeah. So, yeah. And today, as I said, I have two parts. One is about creative AIs. The other side is protective AIs. And we both believe that are important to create a new ecosystem in the music industry, music field, as well as other fields like movie or gaming industries. So I'm gonna start from creative AI part. So this slide, I made this in 2024 when there was nothing like Sora 2 or Veil 3. There was no such thing like sounding video generation. So we kind of, we had some brainstorming and, came up with the idea of sounding video generation, and we thought that this should come. And actually, we now observe, many, sounding video models out there. So, we did great. And I'm just today gonna go through really briefly about how this field has progressed. Here the first thing I want to mention is there are basically two ways to actually achieve a sounding video generation modeling. So one is unified modeling. This is a very straightforward way. So you put audio and video in one model and jointly train. But it's always, difficult to get a lot of pair data. Of course, if you can access to YouTube and download some data, but sometimes sound quality is not good enough, so you need to look for other sources, right? So this is the downside of unified modeling. While there is another way of modeling this audiovisual models. So composable modeling is one really a practical approach. So there are many high quality sound models out there, right? So you just download them, and then a video model and audio model, you download them, and then you combine without retraining those models. So this is called composable modeling. And the pioneering work, I believe it's Cody 1. So Cody 1 is known as the first of its kind composable modeling. And basically there are two ways for this composable modeling. I said without retraining, but fine tuning is actually one way to achieve this. But I want to focus on this guidance part, where you don't actually need any training. Guidance is, I think the word classifier-free guidance or classifier guidance. So basically, given some off-the-shelf generative models, you can actually guide the output to a certain space by using some text prompt, audio prompt, or video prompts. So guidance here is to kind of guide the output so that the two modalities could be aligned in the end. So diffusion is an iterative process. So while during the iterative process, you use this mechanism and guide the output, so so that two modalities could be aligned well. And guidance, module could be anything, any classifiers, like image bind is one good example, and I'm going to introduce that next. And so classifier-free guidance, I'm not going to explain that because, you can go to our monograph and you see a lot of explanations there. But I want to, introduce this pioneering work, diffusion posterior sampling. So if you have a, constrained math already, then you can just impose that to your update rule of diffusion inference. And then, so this M refers to manifolds. And then, so M4 is the earlier iteration, and then you could go to M3, M2, M1, M0. But you could also impose this Y A of X, and then it works as a guidance, and the generation goes to that direction. So this is how it works, and often used for inverse problems. And this work is the one actually that uses image bind for guidance. So image bind, I'm not sure you're familiar with this, but it's a variant of extended version of clip or clap. So it has three modalities, four modalities. So text, image, audio, and videos. So they are all trained, aligned well. So you can use it to semantically, align the two modalities, more than two modalities, of course. But here you want to align audio and visuals. So so this doesn't actually require any additional training, and you can see the output aligned well semantically but not temporally or spatially. So that's the that was the problem of seeing and hearing. The work was done in 2024, so there's some follow-up works. And this one, yeah, it's from our lab. We call it MMDisco. So we found some problems using when we use image bind for guidance, and especially the temporal alignment. So we came up with this idea. We train a discriminator, like GAN's discriminator, and let the model to classify whether the output is well aligned in time or not. And how we train this discriminator is you feed real data and fake data, right? And for real data, you actually feed real videos, audio, visual data, because it's perfectly aligned normally. But of course, you need to filter out some video with music or video with off-screen sound, right? And then for fake data, you just randomly, pair two modalities taken from different, videos. So yeah, that's it. And as soon as you train this discriminator, you use it at the inference time, and then the model knows how to go to the right direction. So this is MMDisco and accepted at ICLR this year, yeah. And this one was presented at Hawaii last month, ICCV25. So this is actually a really specific problem for video generation, but of course it's also the case in audiovisual generation. So if you simply apply DPS, diffusion posterior sampling, to this problem, since this requires back propagation, you need a lot of memories, and this is often the problem in academia, right? So we came up with this idea. Rather than doing a back prop every iteration, we just go diffusion inference first, and multiple times you do multiple diffusion inferences, and then you select some good examples by using the classifier you want to integrate, right? And you can see which output are doing better than others. So how they moved along manifold. So you can actually know the directions from them, and then you can take average of them and use it for the next step. But yeah, you can actually compute any ways to get optimal, better direction. So it's called Titan Guide, and we tested and in audio guided video generation, and we observed that Titan Guide actually it's more efficient, but it performs better than seeing hearing. So yeah. And in terms of memory, I hope you can see the graph, the left, so there are some models, popular models in image space, and compared to them, Titan Guide, the memory size is half or more than half, so it's very efficient. And also FVD, the metric, like FID in image, and you have FAD in audio, right? So FVD is for video, And we all agree that FED is not the best, metric to use to evaluate the fidelity of videos, but this is a standard, so we use it, and it shows that Titan Guide is really doing well. And I would like to change my topic from audio-video joint generation to video-guided audio generation, sound generation. So I think, to my knowledge, Deep Foley is the pioneering work using diffusion for this task. So it's called Deep Foley. And it basically applied the same approach in text-to-audio space or text-to-any generation technologies. So rather than using clap kind of thing for encoders, here they train their own contrastive audio-visual pre-training model. So it's trained in the same way that clip or clap were trained. So they first trained this CVP model, and then just simply condition on the diffusion generative model. And the diffusion part was simply trained on audio. And this works like that. So it doesn't work in the opposite way, like you cannot feed audio to this model and get video generation. This is dedicated to video to sound. And this V2A mapper, there are several other works like this, but I want to introduce this one because it's the structure is very simple. So V2A mapper, so as you can understand from the name, actually map the embedding of clip to the embedding of clap. Right, and then once the embedding has been converted to other embedding, then you can simply run a text-to-audio, and it could be off-the-shelf models, any models. So this means that we have access to some high-quality text-to-audio, text-to-sound models, so we can leverage them, right? So this is an interesting study. And this one is from us. So the previous work using high-quality text-to-audio models has some limitation, like we cannot change the architecture of models, right? But we know that text-to-audio models tend to have really high quality because pairing text and audio is easier than pairing audio and high quality sound. So we decided to incorporate text audio pairs into our training. And here we used audio, visual, and text data sets, and also audio text, but here the high quality audio and text data sets. And then we put them into our, DIT models, and then MMAudio was trained like that. I want to. So first of all, I'm gonna play this demo, and the video part was made by some really nice model. I forgot the name. It might be Veo or Sora. Sorry that I'm not familiar with that, but the audio was fully generated from MMAudio, given this, this video. So let me play back. really like to see faces when you're watching this video. Yeah, yeah.
What was the input?
Input is the generated video, yeah, to MMAudio, and then just get the output. So this is also from us. So we extended this MMAudio to support, so that the model could support separation as well, without, we only fine tune the model without going into any retraining from scratch. We just used MMAudio as a pre-trained model, and then gave the mixture as an input to the model, and isolated stem to the output of the model, and then fine-tune the model. And the interesting observation is that even though this model is fine-tuned to achieve separation, when we feed random noise to the model, it can still generate sound. So it has two capabilities, actually. So it can generate sound like MMAudio does, and it can also separate sound when the mixture is the input to the system. So we call it MMAudio SEP, like audio SEP. And this one, multi-foley, it was a concurrent work to MMAudio. It's from Adobe and presented as CVPR. The nice feature of multi-foley is that it has a lot of controllability. So it has actually audio control, like you can feed reference track and then let the model to align audio and visual. And also the model can extend audio given the audio prompt. So this kind of thing, it was not possible in MMAudio. So yeah, multi-foley is really nice work for sound creators or sound designers. MMAudio, I would say it's rather for video creators. So someone who don't want to spend their time to create sound, it's a nice tool because you just press one button. But for sound designers, I don't think it's sufficient. Sound designers want to tweak, sound. So I think multi-foley is doing a really good job. And there's a benchmarking work from us together with CMU. Christonafu's lab, actually it's called Foley Bench. And unfortunately, the paper is still not open, but the website is there. So yeah, you can find the link from the QR code. And what we did is actually the benchmarking data set is often VGG, right? And the problem is the VGG has some music videos or off-screen sound in the videos, so it's useless to evaluate video to sound systems in terms of temporal alignment or spatial alignment, right? So we kind of filtered out those, unrelated videos, and then created dedicated data set for these tasks. And we actually surveyed many metrics used in different papers. So we aggregated everything, and we can now comprehensively evaluate many different models. So what's next for video to sound? We believe one avenue is this way, so spatial access. So now all the models can generate high quality sound, but most of them are monaural. So in the professional studios, people don't use monaural, right? People want to have stereo or modern stereo sounds, and the stereo sync is for stereo, but these are presented at ICLR. It's ambisonic format. The output is ambisonic format, so it's already supporting 4 channels. But we see higher order ambisonics maybe in the future, or other type of format like binaural or other stuff. So this is one avenue, I believe. And of course, benchmarking is lacking. So the Foley bench can only evaluate monaural output. But here, when it comes to stereo, spatial, or audio, there's nothing right now. So we actually developed this SAVG bench, spatial audio visual generative. I forgot, but this one, it doesn't use LLM or some kind of popular methodologies, but we simply used object detection and also sound event localization and detection technology, and a CD alignment, spatial alignment. Yeah, it's a very straightforward and simple way. So we know that this is not the optimal way to evaluate. We could have one model to evaluate both, but this is our starting point. And this one, so I already talked about what's the next, but I think this interactiveness is also the next step. So
this ocean, it's a force, a wild, untamed might.
So we already
and she
see
commands your awe
some models,
with every breaking
sounding
light.
video
It's
generation
a
models.
force, a wild,
What's the
untamed
next?
might.
So we believe interactiveness here is that it means like so to achieve that we need some very low latency models. Otherwise, we cannot convey a user intent to the model, right? You cannot interact with the model. So all the models take whole spectrograms and then output the spectrograms, right? But frame level online sound generation was not there. So we recently developed a model called Sound Reactor. So this one actually receives previous audio frames and also previous video frames as well as current video frame, and then output current audio frame. So I hope you can hear it. So actually, I need to tell you that this demo is not interactive demo. So ideally, every time I push this button, sound become different, right? Because it can run in real time and low latency. But I haven't, implemented that kind of application yet. So this one is pre-recorded, right? Yeah. So where we use this is, for example, in game, right? You have hardware and GPUs are there, so you can actually deploy this model and GPU and then let the model to generate sound as soon as the model observe, next frame video frame, right? So, and another thing I want to, I had a link to the paper, but I forgot. This one is, not. I don't believe actually this is not related to video to sound. it's actually the text-to-sound real-time version for artwork. And actually we did this collaboration with a sound artist, Japanese sound artist, Evala. The picture of him is there. We deployed our real-time sound generation based on a SpecMasked model presented at ISMIL. And we used 8 loudspeakers in the space. In the middle, the photo is really the visuals of the space. But behind the wall, there are 8 loudspeakers, and each loudspeaker receives different text prompt, and also receives audio prompt. But the audio prompt part is universal, so it just receives the same sound made by the sound artist Evala, and the system generate, sound. And all the 8 loudspeakers generate different, sounds. And it continued for 4 months or something. I was in Japan when the event started, so I know how the sound was like, but I was not at the end, so I'm not sure how it ended up. But it can continue forever, actually, because it's real time, right? So next, protective AI parts, and I need to check if I'm doing good in schedule. So how long do I have? I don't have 15 minutes. Okay, I need to go quickly. Yeah, so I think you all do SNS, right? So, and you saw these videos or images. There are a lot of problems, ethical or legal problems in modern generative models, audiovisual generative models. And as a community, we want to solve that with, also with AI technologies. So I briefly categorized problems into 3 groups. First one is about copyright infringement. So not sure whether you are familiar with this anime stuff. So it's the Demon Slayer. Yeah. So the main character of Demon Slayer can be easily reproduced from certain model, and I think this creates some problems with content holders right now. I hope it's solved soon, but this is the first one. So copyright is the issue, or some other rights. And the second one is a style. So it's a famous effect called Ghibli effect. So if you use Ghibli effect, then you can convert any image to this style, right? So, and also style is known as a property that could not be protected by copyright. So you cannot apply copyright to style. So that creates some difficulty between the AI companies and content holders. And the third one is memorization, and this one especially about verbatim memorization. So it actually regurgitate the training data set, and I think this one is out of question maybe. So even if the content holders and the AI companies file some contract, typically in the contract we explicitly note that regurgitation should be prohibited. So we observe this, so we should tackle this problem. I think this one is a rather obvious case. Others is a matter of legal, ethical stuff. So people think in different ways, right? And the first one, so attribution. So rather than opting out from the system, content holders actually ask model providers whether they can monetize from it. So licensing, right? But to accomplish this, we have some problems. So if you simply apply some matching, image matching or video matching or audio matching technologies here in data space or in latent space, we end up with finding this irrelevant images because they, AI is not trained to catch this character in the image. So we came up with a solution that it's diffusion based, but we can actually find this concept in the image and then attribute them. And this is a unique problem in video. We don't have this kind of problem in music space, because music, we just want to attribute to one song, right? But in video, we see some characters there, so we need to find that character in the image or videos, and then connect, establish the link. So the second one is style imitation. So there is a popular way to avoid this. It's text filtering. So you can prohibit writing Ghibli in text prompt. But there's always a way to circumvent, right? So go around. So it's also possible at the inference time to avoid this problem. You can, throw a negative prompt to the system and let the model not generate anything similar to here Van Gogh, but Ghibli or anything that that could become a problem for animation studios or movie studios. And the third one is about memorization, and we have not this one. So this one actually, the NeurIPS work actually revealed that only a single neuron can memorize one image. So this one was done in image space, and we also saw this work from Merle. In a famous model like Tango actually suffers from memorization. So they found that the spectrograms from one from Tango, another from the data set, they look totally similar. So there is a problem. And at CVPR this year, we kind of proposed a solution to avoid this problem at inference time. We found that the magnitude of a conditional noise prediction can actually tells us where we should use classifier-free guidance and until which iteration we should refrain from using classifier-free guidance. So we call the point the transition point. We call it transition point, and this point can be decided by observing the magnitude of conditional noise prediction from diffusion model. And also we highlighted this red or magenta section attraction Bayesian. As long as the output is in this field, it suffers from memorization. So this one is memorized, memorized output, and this one is input. So and it's from stable diffusion. So yeah, this stable diffusion has this problem in this level, at this level. But after this transition point, if we use classifier-free guidance, before that we just do unconditional generation, and then we could get this image. And this also aligns with well with a text prompt. And this one is totally unconditional, so this cannot reflect the user's intent. So the interesting point is how we can know this transition point, right? And the ideal case is transition point comes to here. So this is the actually the diffusion step. So you start from, let's say, 80 for image or 79 for image, or now you can use flow matching, and then 28 or 8, and then gradually denoise the output, right? So ideally, this transition point comes to the starting initial noise, iteration. So we saw the kind of follow-up work we will see at this year's NeurIPS. So this graph on the left-hand side actually shows the magnitude of conditional noise prediction. So we can decide this attraction Bayesian field, and you see on top, one is training image. Another, similar image is the generation from the model. And if you start classifier-free guidance when you're in a red zone, then you end up with this image. But right after this transition point, then you have different image. And the authors actually conducted some empirical experiments, and saw that this right-hand side graph observation. So by changing initial noise, then transition points actually moved. So they developed a way to optimize the initial noise. It's in the paper, so I'm not going to explain that. But we can move this transition point to here, in this case, 1,000-step point. So it's the beginning of diffusion iterative process. So I need to go quick, I guess. So just want to also talk about music space. So according to the latest Deezer report, it seems like 28% of music on the platform are AI generated. And within only 6 months, this percentage increased by 10%. So another 6 months, we'll see 38%. And another 6 months, you see 48. Might be more than half. So yeah, this is the current state. And of course, we see, the right graph in 2030. This might be the, optimistic scenario. So people in the community believe that compensation to artists is really needed. Otherwise, they lose their jobs. So attribution is, of course, obviously one best way to remunerate to artists. So popular way to do this is to use some matching technology, right? You see similarity between the generated music and training data set, and compute some contributions. And it's always difficult, right? And it's not, there's always a discussion, like similarity is really the good metric to measure the contribution of someone's work in the generated output. So, yeah, I think this discussion has not been, finished. We need some further discussion, but I see many other problems like this one. I call it first generation text-to music. So the modern text-to music, I call it first generation. It's because it's trained on human-made music only, right? This is the state, and the input is mostly text prompt, and the output is music. But you see this in the future, nth generation text-to music. The one was trained on synthetic music, and you see the derivative, right? You see a lot of other models in the training space. The songs are generated from different models, so it becomes harder for us to track back to the original training data set. So this is one big disaster, but there's a reason why we don't observe this at the moment. It's because there's a phenomenon called model collapse. So if you train a model fully on synthetic data, actually the diversity of the output degrades. So you cannot do that unless you solve this problem. So yeah, this slide actually showed, this one is in LLM, so the perplexity of the generated data points are shifted, right, through the nth generation. So generation 0 is nice, but after generation 1, you saw this graph. So is there any way to solve this, problem? Not the model collapse problem, this problem. So nth generation problem. Actually, there is a way to do this, and we call it attribution by design. We have a paper on this. So rather than, checking the relevance correspondence between training data set and generated music, why not let the artist opt into the system? Why not provide the artist songs to users? Of course, artists need to agree on this, but why not proposing songs to users and let them select songs, right? And then attribution can be easily established because we know that from the system. Here, the user selected artist C and artist E. The combination of two songs might, cause some other type of discussion, but technically speaking, it's possible, right? So you mix two songs and let the model generate songs that reflects two different songs flavors. So yeah, this is one way to solve the nth generation attribution problem. So that's it. Yeah, sorry that I took so long, but that's it from my side. And this is a QR code to my demo page. And this one is to my personal SNS. So please, send me invitation. Thank you.
So very nice talk. So one sort of general question I have is whenever you're trying to create something from video or from some physical scene, sound usually there is a sort of an underlying propagation model. Of course, most of these AI-based approaches do not necessarily explicitly respect the physics. So do you have any ideas how your diffusion models or other techniques can be made to respect the physics of propagation?
Yeah, thanks for a great question. Actually, there is a field for that, physics-informed video to sound generation. It respects physics in the modalities. Actually, most of them I presented don't care about the physics. So yeah, there's another line of work there. Yeah. Thank you.
Thanks, Yuki, for the very nice presentation.